Let's analyze and solve the best time to buy and sell stack coding problem. We are given a zero-base array prices. The array is unsorted, where the prices of I is the price of the stack on a day I. And we have to return the maximum achievable profit from a single buy-sell transaction, or zero if no profit is possible. In the terms of coding, we have to write a function, let's call it max profit, and the function will have one parameter called prices, and it's a vector of ints, and we have to return max profit, so we will be returning an integer value. We are also given a set of constraints. The most important observations from those constraints are that the prices array is never empty, and that the price inside the array is either 0 or positive integer. To summarize, we must buy before we sell. We are only allowed one transaction, so one buy and one sell. If we cannot make profit, we have to return 0. And the important thing to notice is that we are asked to return maximum profit, not the buy and sell days. And that's pretty much our problem. To solve this problem, we can start from a simple brute force approach. So let me copy the array from example 1. And what we can do, we can try to buy at each and every day and sell in any of the following days. What do I mean? Let's say we purchase our stack on day 1 or at the index 0 in our array. Let's mark it as a purchase index. And then we will try to sell this stack in every following day and see if we can make profit and which profit is a maximum profit. So let's track our maximum profit, max profit, and we will start from 0. And the way we compute the profit will be as follows. So it will be profit equals sell price minus purchase price. And using this formula, let's try to go through that example and see if we can make any profit. So let's introduce a second index. Let's call that index sell index. And we will use the formula. So we have to compute the profit. Sell price is 1 minus purchase price is 7. So our profit is minus 6. And this is less than 0, so we will discard this profit and these 2 days. And we can go to the next day, so we will move to and try to sell on the following day. So our sell index will be here. And again, we will compute the profit. Profit will be sell price, which is 5, minus 7 is minus 2. Again, is less than 0. We will discard this transaction. And we can go on until we reach the end of the array. But if we notice that the 7 is the highest number in the array, we can understand that starting from 7, we will never make profit. So if we do this one by one, we will end up having always a negative profit. So in this case, we just move to the next purchase day. So we will move our purchase index to the next day. So purchase index is now here. And again, we will have a sell index and we will try to sell at any possible later day. So sell index. And let me erase those. So in this case, our profit would be sell price, which is 5, minus purchase price, which is 1. So the profit is 4. 4 is greater than our current max profit. So we would update the max profit and make it 4. And we would move the sell index to the next day and compute another profit. So it's gonna be, we are selling for 3 and we purchase paying 1. So the profit is now 2. Current profit is less than the max profit, so we are not going to use those 2 days for our transaction, and we are going to move the sell index to the next day. And again, we are going to compute profit. The profit will be sell price, which is 6, minus purchase price, which is 1, equals 5. This is greater than max profit, so we are going to update the max profit to 5 And the process will continue. So the main idea is that we will be trying to purchase at every possible day and compute every possible profit. And if our profit is greater than the max profit, we are going to update the max profit. So in this brute force solution, we are basically testing every possible buy-sell combination. And because of that, our complexity is not very good. The complexity is O of n squared. For each day, we have to process every other day. So we will end up in the situation when we have two nested for loops. And this is the n squared complexity, where n is the size of the array. The space complexity is very good, is O of 1. We are not using any additional memory. And that's pretty much the brute force solution. The brute force solution works, but we can do better. And let's use the same example array. In this approach, we'll be tracking again max profit. We will start from 0, but we will also be tracking the minimum purchase price. And we will initialize it with the first value in our array, which is 7. And the profit will be computed as follows, which is the sell price or the current price we are considering minus our current minimum purchase price. So here is how this is going to work. We will start from day 1. We are going to check whether the current price is less than our minimum purchase price. It is not. So we are going to compute the profit. The profit is going to be equal 7 minus 7, which is 0. It's not greater than our current max profit, so we will not be updating max profit. Then we will just move to a next day and repeat the steps as we described before, which is we will compare whether our current price, which is 1, is less than minimum purchase price. It is less, so we are going to update the minimum purchase price to 1. And then we will compute the profit. The profit is again 1 minus 1 because we just updated the minimum purchase price, which is 0. This is the same as the max profit, so max profit is not going to be updated. We will move to the next element. We will check whether the current price 5 is less than our minimum purchase price. It is not, so we will compute the profit again, and the profit will be 5 minus minimum purchase price is 1, so 5 minus 1 is 4. 4 is greater than 0, so we have to update the profit. So max profit is now 4. We'll move to the next element, which is 3. Again, we will compare whether the 3 is less than our current minimum purchase price. It is not, so we will just compute a profit. Profit is 3 minus 1 equals 2. This profit is less than our max profit, so nothing will happen. We will move to the next element, 6, and we will again update the minimum purchase price. So the current price is 6, not less than the current minimum purchase price. So we are not updating the purchase price, and we will compute a profit. Profit is 6 minus minimum purchase price equals 1, so it's 5. 5 is greater than 4, so we will update the max profit, and we will move to our last element in the array, which is 4, and we will repeat the steps. So 4 is greater than 1, so we are not updating our minimum purchase price. We will compute the profit. 4 minus 1 equals 3. 3 is less than 5, so max profit is not going to be updated, and we reached the end of the array, so our result will be 5. Which is the proper maximum profit we can achieve using the data in the array. And the complexity of this algorithm is O of n. We just have to process that array once. And the space complexity is of O of 1. And this is big improvement comparing to our previous result where the complexity was O of n squared. And that's the optimal solution for this problem. Let's write code for our brute force solutions first. So we'll store the size of the prices in a constant. And we will need a variable to track the max profit. And now we have to process the array. So let's write a for loop. And the first for loop is for the purchase. And for each purchase, we will have to try to sell it on the following day. So we need a second for loop. And the second for loop should start on the day following the I, so I plus 1. And now we need to compute the current profit. And the profit equals the sell price, so prices of J, minus the purchase price. And the last step is to compare the current profit with our max profit and choose the bigger one. So if our max profit is less than the current profit, we will update the max profit. And at the end, we have to return max profit. Let's try to build this code. The build was successful. So now let's try to see if our tests are passing. I have around 20 tests written for this problem. Oh, I see I have a small bug. It should be J++. So let's build it again and let's try to test it. And all the tests passed, so we have successfully coded our brute force solution. Let's write the solution for our optimal algorithm. We need to track the maximum profit, so int max profit equals 0. We also need to track minimum purchase price. And we are going to initialize minimum purchase price to maximum allowed integer. So I'm going to include limits. And we are going to initialize it to numeric limits of int max value. And this will simplify our for loop. And also it will protect us from the cases where the prices is empty. So now let's process the prices. And what we have to do first is to make sure that we update our minimum purchase price. So the easy way to do it is to basically take a minimum of minimum purchase price and a price. Now we have to compute our current profit. And we will compute this by subtracting a minimum purchase price from the current price. Now the last step is to update the maximum profit. So the maximum profit will be the bigger from the profit and maximum profit. And we have to return the maximum profit. And that's our optimal solution. Let's try to build it. It builds correctly. So now let's try to run tests. And all the tests are passing. So that's how we can code our optimal solution. As a last step, let's make sure that our code passes all the LeetCode tests. So first I'm going to paste the brute force solution. And let's see if it works. It works. So let's try to submit this one. And we got time limit exceeded as expected because the brute force solution is not optimal. So for small cases, the tests are passing. For a big case like they have in LeetCode, they fail. So with that, let's try our optimal solution and see if we get any better results. I'm going to replace the brute force solution with our optimal solution. Let's see if it works. And now let's see if we can submit this one. And we were able to pass all the tests, including the tests with a large amount of data, and the time is very good. This is the end of this solution. The source code is available in the GitHub repo shown on the screen.